Okay, so please stay for the class. Don't go. But it's so you can have this as a reference for when you study, okay, for the following tests. Okay, so I'm going to start sharing my screen. Dun. I have. Okay. Okay, so I'm going to start off by, might need more slides. Okay, so we're going to start off by talking to you a little bit about the Talmadge and Fitch method. Okay, so let me take you out a pen. So we're going to start off with the Talmadge and Fitch method. You guys see that I'm writing on the board or on the slide?
Yes.
Okay, good. Okay, so we have a Talmadge and Fitch method, and as I said, can't find me here. So as I said, this method, the objective of this method, is is the sizing of thickeners. Okay. Remember that we have two types of settling systems. Remember that we have, on one side, we have settlers that are for the settling of suspended particles. Okay, and that on the other side, we have thickeners. And when it comes to tailings, for example, this is where we use these thickeners. They're focused on producing thickened slurries. Okay, so what is the basis of the Talmadge and Fitch method? The basis is the following. Let's say we have a batch settling experiment with characteristics of the solid that we eventually want to size a thickener for. So over time, when we have a settling column, for example, okay, this is a settling column. At first, or at T1 equals 0, when we start the experiment, we're going to have in this column that has a certain H0 as a height, we're going to have some suspended particles here that are going to be uniformly dispersed. And at T equals 0, we're going to have a C0 concentration of particles. And this concentration is in kilograms of solids per cubic meter of suspension. Okay? Now, over time, because of the action of gravity, these particles are going to start to settle. So let's say that at T equals T1, a supernatant is going to, there's going to be an interface here. I'm going to call it this H at T1. And this would be the interface height, where the same particles are going to be in this area, but now a little bit more concentrated. Okay, because since we're settling, now we're going to have a C, let's say at T1, that's going to be higher than C0. Okay, and here at the top, it's just liquid. Now, if we keep moving, okay, this is going to settle even more. So we're going to have another height at, let's say, T2, where particles are going to be even more concentrated, but at the same time, I'm going to have solid at the bottom that is going to be highly more concentrated or compacted. Okay? And after a while, when we reach our final settling time, or our when we achieve a desired concentration at the bottom, desired concentration T sorry, Cu, and U as in underflow. Okay, let me erase something. Okay. We're going to reach that at a certain height that we're going to call HU, and at the top we're just going to have the clarified liquid. Okay, so the basis for this process is that the solids that are settling throughout the column, since we're talking about batch settling, the total concentration load, the solid load, and by solid load I mean the overall amount of solids over square meter. For example, I mean the overall solids in a certain area, because these columns are generally either like this or like this. Okay, but overall we're going to have the same area here. So the solid load over time, or over these different scenarios, is going to be constant. So in that case, we can say the following. We can say that the solid load, or the concentration at any given time, times the, is it the height? I think it's the height. Let me find, yes. Times the height at a given time is going to equal, is going to be constant, okay? So we could say, for example, that at time 0, C0 times H0 is going to be equal to this solid that we have here at the bottom. Cu times Hu. So the Dalmat-Fitch method focuses on determining this final height, which is going to occur when we reach a certain concentration. So Hu is going to be C0 times H0 divided by Cu. Okay, so this is initial data, which would be the design data, because this is the data, especially this one, this is going to be a design parameter, because it's going to be equivalent to the concentration of whatever enters the settling tank. And Cu is going to be also a design parameter, because it refers to, as I said, our desired underflow concentration. Please let me know if you have any questions, because since I'm a little bit concentrated on the board, I can't see if you're raising your hand or anything. Okay, so if you have any questions, just let me know. Okay, so how do we determine this HU and indefinite, the time in which we reach this? Okay, because with this, we're also going to be able to do some calculations. This is how it's done. So we're going to have experimental settling data. Okay, in which basically what is done is that you have a table with time and the height. Sorry, that doesn't have to be a U there necessarily. We have time, we have height, Okay, so we're going to have T0, H0, T1, H1, which is going to be less than H0, of course. Okay, so with this data, we can build a, that's supposed to be straight. Let's try again. This is awful. So what we're going to do, we're going to try here. Okay, so we're going to, what, that was worse. Why am I such a bad, let me see, let me turn over this side. Maybe this will work. Okay. So we're going to plot this data. Okay, so assume that that's straight, okay? We're still going to do an exercise so you're going to be able to look at this properly. Where we have height here, the time over here, and we're going to have, we're going to plot this data. And this is going to turn out to be something like this, okay? Now, what do we do now? And for this, I'm going to use the straight lines from, that are provided by the PowerPoint. So I'm going to leave this. I'm going to keep my notes. And what I'm going to try to explain here is the following. So here we have the experimental data. So what we do now, in order to remember that our goal is to determine HU in order to, and this can be done experimentally, okay? Or we have this data and then we identify CU here, but that's what we're going to look at now. Okay, so first, I'm going to draw a straight line in the first settling zone where the particles are settling at their maximum speed, okay? So first I'm going to draw a line, a straight line that passes through this, this area over here. Then I'm going to draw a straight line where I can see that the concentration or the height is no longer increasing. So this is supposed to be a straight line. It's parallel to this. Okay, it's parallel to this. I'm going to write something here. Parallel to, parallel to the x-axis. Okay, but this is the line that indefinite where you see that the height is no longer diminishing. Then what you do is you draw an angle bisector over here. So here you have to divide this. I don't know how much this would be in terms of angle, but what you do is you draw a line in which you divide this angle by 2 and, in half, I guess. And okay, let's say that's, yeah, you'd say that's similar enough. Then you draw a tangent line to this. Remember that this is going to be taped, so okay, so we're going to draw or try to draw a tangent line to that point over there. And that point, just so you know, is called critical point. Okay. Now with this over here, okay, then finally, we're going to take this formula over here, which is, we're going to do an exercise. So once we do the exercise, this should be much more clear. This is going to be that HU is going to be C0 times H0 divided by CU. Remember that these are all parameters that we already know. So then I'm going to locate HU over here. And then with HU located in the y-axis, Okay, I'm going to draw a straight line, and the line that intersects with this with the tangent line, this is the point that we are going to identify as TU. Okay, so this is the time, in theory, this is the time where the desired height is reached, where we reach the desired final concentration that we want in the underflow of our settling system. So what do I do now with TU? This is where now I can calculate the area of the settler. Now, before I do any of that, I want to try something. I want to see if I can sort of move this around so this is straight. No, I think I messed everything up. Wait. I messed it all up. Wait, let's try again. No, I messed everything up. Okay, let's just leave it as is. Okay. Okay, so what am I going to do now? What are we going to do now with this TU? TU, we're going to use this now to calculate the area. And this area is going to be calculated as follows. Okay, so now with TU, I'm going to calculate the surface loading rate of solids. And remember that that is equal to, similarly to what we saw in settlers, okay, I hope you saw the exercise, as the mass, the solids rate divided by TU, okay? And we're going to call this parameter G T, okay? And this is going to be in units of kilograms of solids over area over time, okay? And finally, this is the parameter that we're going to finally use to size the settler. But I'm going to do it through an exercise, so it's a little more clear than what I'm saying now. This is what you finally use to calculate the area of the thickener, sorry, thickener. And in consequence, that's what we can use to calculate the diameter. Okay. So having said this, I'm going to do an exercise now, and I think that with the exercise, everything is going to be a little bit more clearer, but I needed you to firstly understand the basis of the method, okay? Okay, so now I'm going to stop sharing my screen, and we're going to move on to the exercise, okay? Okay. Where are we? Okay. Now this exercise, no, this is the one I wanted to share. Okay, so the exercise that we're going to do is already published in Aula if you want to download it, okay? If not, we can just keep paying attention and doing your notes, okay? And filling in your notes. Okay, so let's go back here, and now I'm going to share the screen where I have the exercise written. Here it is. Okay. So this is the exercise that we're going to do now. It says as follows: a copper concentrator plant in Chile wants to thicken its tailings in order to recover water back to the process and deliver a lower moisture content tailing stream for disposal. A batch settling test in a graduated cylinder is carried out with flocculated tailings in the interface height, mud, clear liquid, that's the interface, is recorded over time. So here is some problem data, okay? The initial slurry height, the initial solids concentration, the solids density, the liquid density, so you can infer that that's water. Okay, the target underflow solids concentration. So this is the underflow solids more than concentration. This would be percentage of solids, target underflow solids, percentage of solids. Okay, the feed volumetric flow rate and the feed solids concentration, which equals the initial solids concentration of the settling system. Okay, so basically we are sizing for these conditions for the conditions that we would have in the field. This is the experimental data, okay? And these are the different things that you have to calculate. First, plot the height versus time and locate the regime change. Calculate the mass of solids per unit area. Calculate the design underflow concentration. Obtain the target height. Calculate the tangent at the change of regime and find TU. Calculate the limiting solids flux, GL. This is the, well, we're going to look at it now. Size the thickener area, calculate the thickener diameter, and verify the surface or superficial liquid loading. And that's optional, okay? Okay, so first, now what we're going to do is we're going to work in our Excel spreadsheet, okay? In order to plot these and find all the parameters and calculate everything as we're supposed to, okay? So I'm going to stop sharing this and I'm going to move over to the, I'm going to move over to the Excel sheet. Okay. Okay. Are you looking at my Excel sheet? Yes, no.
Yes, yes, yes.
Okay, thank you. Okay, thank you. Okay, so what I did here is the data here is already plotted. Okay, so we don't have to waste time on that. So now we're going to move on to the things that we are being asked to do. Okay, so I'm going to move this over here. I'm going to start calculating some things. Okay, so first of all, we are going to so one, plot, check. Now two is the mass of solids per units area. And let's see if I can take a pin out here so I can dibujar. Yes, this is letting me draw here. Let's do it in blue. So what the mass of solids per unit area, okay, is calculated. We're gonna call this M, and it is calculated as the initial concentration times the height, the initial height. Okay. Okay, and this, if we analyze this in terms of dimensions, this would be kilograms of solids per cubic meter times meter. For example, if we work on this in international units, so and those get cancelled out. So M would be the mass solids per unit of area. Okay, so that would be the kilograms of solids over square meter. So if we calculate this using the data that we have, remember that C0 was, I'm going to look at it in my screen, but I'll let you know now, is 80 kilograms per cubic meter. And the initial height is 1.2 meters. So our M is 80 times 1.2. So, and that would be 96 kilograms per square meter. So we have the first thing now calculated. Let's move on to the third point. So the third point is to calculate the design underflow concentration. Okay, so what we have as data is the percentage of solids, which was 8%, but that isn't the concentration, because concentration, I'm going to use a pen now, because concentration, remember, is in units of kilograms of solids over cubic meter of slurry. Okay? Okay. So this design underflow concentration is going to be calculated as follows. It's going to be the percentage or the fraction of solids times the density of the slurry. So if we analyze this dimensionally, this would be kilograms of solids over kilograms of slurry times, and this is the density of the slurry, this would be the kilograms of slurry over the cubic meters of slurry. Sorry. So these two get cancelled out, and this results as kilograms of solids over cubic meters of slurry. So now what we need to do is calculate the density of the slurry. And the density of the slurry is, because remember that if we look at the data of the problem, I'm just going to move back to, oh wait, I'm going to do a little thing here. Wait. Give me a moment. I'm going to copy and paste the, okay, this is the problem data. I'm going to copy and paste it over here so you don't have to go back to the document every second. Okay. So as you can see, we have the liquid density, and the solids density, but we do not have the slurry density. The slurry density is calculated as follows. It's calculated like 1 over WS over, the fraction of solids over the density of solids plus 1 minus the density of solids, which would be the density of the liquid over the density of the liquid. Okay? Okay, now with all of this, we are going to do the calculations in the spreadsheet. Okay, so let's start here. This would be first the density of the slurry. This is going to equal, 1 over, this is what we wanted. Oh, I'm sorry, made a mistake here. This is the design underflow concentration. So this would be 55%. Okay, not 8%. 8% is the feed solids per percentage. But what we desire at the underflow is 55. So this would be 1 over 55 over 2,650 plus 1 over, 1 minus 55 over 1,000. Yep, I think I require a double parenthesis. Yeah, I don't know what I did. Okay, but that's the correct result. Okay. And this would be kilograms per cubic meter. So now, in order to calculate the concentration, Cu, this is 55% times 1,521, and that would be the solids concentration, okay, in kilograms per cubic meter as well. Please let me know if you have any questions, okay? Okay, so now we're going to move on to exercise 4, or point 4, which is, I'm going to copy and paste this as well, so we don't have to start moving back to the documents every second. So here is what we have to do. Point 4, so for now, we have, okay, so now we have, this color is nice. I like this one though. This one's like a nice color. Okay, so we already did this one, we already did this one, we already did this one. So now we have to obtain the target height. And now this is where we, oh no, we're still calculating. Okay, we don't need to use the graph yet. So point 4 is obtain the target height. Heights. So as I mentioned earlier in the class, okay, the basis of the Talmadge-Fitch method is that the solids over time within the overall solids, or the total solids over time in a settling system is not going to change. So here what happens is that C0, that's awful. I don't know how we, oh, here, I can erase it here. So cool, though, all these tools that we have now. Oh, I know what happened. Okay, so this would be Z0 times H0 going to equal Cu over Hu. So what we have to calculate now is Hu, and that is going to be calculated as C0 times H0 divided by Cu. So in our case, we already have all the data, okay? Cu was calculated in the previous exercise, and C0 was the 8 kilograms per cubic meter. So 8 kilograms per cubic meter. If we look at it in the data, initial solids concentration 80. Oh, sorry, it's not 8, it's 80. Okay, 80. And the initial height is 1.2. So, and we calculate HU as C0 times H0, which is something that we already calculated in the first exercise, remember? Divided by this number over here. And what comes out is too many significant figures. I'm going to diminish these, reduce these a bit. Okay, so it's 115 meters, which is equivalent to 11.5 centimeters. Okay. So now we have all that we need to start calculating 0.5, which is draw the tangents at the change of regime, find TU. Okay, so now I'm going to move these out of the way. I'm going to take these out of the way. Eliminate these little things over here. And we're going to calculate the tangents, okay? Okay, as I said previously, there are several ways of doing this, but I think the most straightforward and maybe even easiest method is to just do this graphically. even if it's a little bit approximated, okay? So first what we're going to take is a line, and we're going to draw a straight line in this first area over here, okay, where the settling concentration is the settling speed is the fastest. So we're going to draw a line, or the best as we can, I guess. Okay, that's it. Where, as you can see, we're passing a straight line through these first points over here where where the settling rate is the fastest. Okay. Why do I say settling rate? Because this is the slope of the height difference over time, and that would give us a settling speed. And then we draw a second line in the zone where we can see that the height of the interface is no longer diminishing. So that would probably, we can estimate this as this final dot over here. And then we're going to just draw a straight line over here. So now I'm going to change color. Let's try red. I don't know if any of you have any problems with colors. Okay. Oh no, that's not what I want to do. I wanted a new line with a different color. Doesn't matter. Okay, so now our third step is to draw a bisector line. Okay, over here. Okay, so I don't know if that's the same. So here you have to sort of like use your imagination or maybe see what the exact angle here is. But I would say this angle here is the same as this angle here. So just to do that, I'm going to locate alpha. So just so it's clear that I'm drawing a line that is, dividing this angle in half. Oh, I don't know what I'm doing. Okay. See, I'm going to leave these little squares over here with the name of the angle. Doesn't matter the angle really. It's important thing is that it's the same. Okay. Give me a second here. Relleno, sin relleno, contorno, sin contorno. You guys are awfully quiet. I hope you're understanding. If not, please let me know. And if not, you can look at the video afterwards, okay? Okay, so here at this line over here, we have identified something called the critical point. And I'm just going to put a little star here. So this star would be a critical point. Critical point that has the purpose of us having to draw here a tangent line. So we now are going to draw our tangent line that is going to pass through this critical point. Now bear with me, I'm doing my best effort in order to draw this tangent line. Okay. Okay, would you say that's tangent? I don't know. I'm doing my best here, okay? Okay, so let's say that that's the tangent line. Okay, so that's critical point. By critical point, I mean the star. And this other line that we drew here is the tangent. Or tangential line. To the critical point. Okay. Perfect. I don't know if it's perfect, but it's good enough, I guess. Okay, so now what we're going to do is, we already calculated here this critical height that was 11.5 centimeters. So we're going to locate this in the y-axis. Okay, so this is 15, this is 10. This says, I don't know, 12.5. I would guess 11 is around here, okay? La-da-dee. So where this line intersects, is intersected to the tangential line to the critical point. Here, I'm going to go down, blah, blah. And here's where we're going to draw TU. There, okay? That isn't very straight. Wait, I'm doing my best here, okay? Please bear with me. Okay, TU, and I guess TU in this case would be 102, 101, would you say? 101. 101 minutes. No relleno, no contorno. Okay. Okay. This is TU, and just so it's clear. No. It's thinking too much. No, 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 no. Oh, well, that was frustrating. Let's see. Let's hope we didn't lose anything. Okay, no, we didn't lose anything. Let me just go back to the screen. Excel suddenly shut down. Office does that stuff to everyone. I don't know why. Okay, I'm going to save this just in case, so just give me a minute. Exercise thickener. I hope I'm not boring you too much. Okay, please bear with me. But I think this is important for us to work out in class. So just so you know, this is HU. Okay, I'm going to share all these files afterwards, okay? Okay, so TU is now 101 minutes, or let's divide this by 60, say that how many hours it is? 1.68 hours. Okay. Okay, so now let's continue with the exercises. As we can see now, 6 is calculate the limiting solids flux. So the limiting solids flux is, I mentioned it earlier, but I'm going to repeat it now. Let's go back to the drawing. This nice color pencil. Okay, so the limiting solids flux, okay, I mentioned it before as the sort of like the equivalent to the surface loading rates. It's going to be calculated as the mass of solids over area divided by TU. Or in other words, this is H0 times C0 over TU. So this is going to be GT is equal to, as I said, I calculated this earlier. So we can use this same parameter over here. I'm going to divide this by 1.68. So our value would be 57 kilograms of solids over square meter over hour. Okay, so the interesting thing is that I'm going to highlight this now, and maybe even increase a little bit in size, because this is going to be our design parameter, or our scalable, scalable parameter for the thickness sizing. By this, I mean the following, that we took some experimental conditions, and now these experimental conditions are calculated or introduced into a parameter, and this is the scalable parameter that we are now going to use to size our thickener. Okay, so 7 is size the thickener area. So now how are we going to do that? Our thickener area, okay, is going to be calculated as our thickener area, since the area, now I'm going to do this properly. The area is going to be calculated as the flow rate of solids, of dry solids, over, okay, this pen isn't working anymore, over GT. I'm going to change the color because it's not working anymore. I'm just going to go back to blue, and I'm going to thicken the pen a bit. Okay. So we're going to calculate this as the flow rate of solids over GT. And if we analyze this dimensionally, this is going to be kilograms of solids over time divided by kilograms of solids over square meter over time. So time gets cancelled out, the solid mass gets cancelled out, and we finally end up with the solids area. Okay? Now, we have to calculate the flow rate of solids in order to do this. Flow rate of solids. So let's look at the data that we have in our problem. Our problem data, as we can see, is we have the feed volumetric flow rate, okay? But it's in volumetric flow rate, and what we need now is the solids flow rate. So how are we going to calculate this? We're going to calculate this the following way. The flow rate of solids is going to be the volumetric flow rate of solids, of slurry, volumetric flow rate of slurry times the feed concentration. So if we analyze this dimensionally, this is going to be cubic meters of slurry over time times the feed concentration, which is going to be in units of kilograms of solids over cubic meters of slurry. So again, these two are going to get cancelled out. I'm going to look at kilograms per hour. Okay, so now let's calculate everything that we need in order to size our thickener. Okay, so first of all, the flow rate of slurry is going to be 250 times the solids concentration, and that was 80. Okay, let's just write 80. No, that's fine. Doesn't matter. Okay. So this is going to be, or this is 20,000 kilograms per hour of solids, and this is just solids. Okay. So now we can calculate the area as the flow rate of solids divided by the GT that we calculated in our first exercise. So that's why I mean, but by this being the scalable parameter for the thickener. So this is going to be 351 square meters. And now 8. Now we can calculate the diameter. And this is really straightforward. It's going to be the square root, raíz in Spanish, square root of the area times 4 divided by pi. This would be the size of our diameter. Okay. And finally, verify the superficial liquid loading. This one's optional, but we are going to calculate it anyway. Okay. Now, this parameter is calculated. I'm going to call it V0. I'm going to write it down. Dibujar, dibujar, dibujar. Okay. I can't dibujar. Now I can draw. So this SLR in terms of volume is equal to the flow rates, the volumetric flow rate. I'm just going to write volumetric flow rate. Going to be the volumetric flow rate divided by the time, the area of the diameter of the thickener. Okay, so in this case, this is equal to volumetric, going to be equal to 250, which is the volumetric flow rate in the system of the feed divided by the area. Okay, and this gives us this gives us 0.71 cubic meters over square meter hour. So as an exercise, okay, so proposed exercise. Oh, I don't know what I'm doing. Let me save this. So as a proposed exercise, compare this SLR to values of thickness reported in literature. Okay, well, this is a proposed exercise. You don't have to do it, but it'd be nice if you could. Okay. Okay. People, students, any questions? Okay. Okay, so yes, please let me know.
Excuse me.
Yes.
I want to confirm that to draw the tangential line,
Yes.
it has to be like with the it has to touch the data points.
Yes. I mean, not necessarily the data point, but the line that is drawn by these data points. Let's see if I can draw a line. Agregar etiqueta, dar formato. Wait. Let's see if I can draw a line here. Lines, solid line. Okay. Not necessarily has to pass through the point, but it does have to pass through the curve. In this case, it doesn't really pass through the point, but it does. No, it does. It has to touch the critical point. Yes, it has to touch the critical point. Then I'm going to change the color of that. Wait. Formas. Let's draw this one. Let's make it orange. So it does have to touch the critical point. Okay. And the critical point can or cannot, be one of the points of the curve, but it does belong to the overall curve. I don't know if I answered your question with that.
Yeah, thank you, Professor.
Okay. Any other questions? Okay. Okay, so now I'm going to look, it's 12:06. So I'm going to ask you to have a little bit of patience or bear with me because I really do want to do the last exercise. We are probably going to finish at 12:30. Is that okay? Considering that you're not going to have classes in the next in the next block.
Yeah, it's okay.
Okay, thank you. Okay. So I'm going to stop sharing and now we're going to go back to the going to go back to the problem statement. Okay. So our following problem is we're going to use the ternary diagram, okay? Okay, so our problem says as follows, states as follows. The increasing pressure put upon, this is just to let you know, this is an exercise from last year's test, okay? So you can start getting an idea of what the exercises that might come up in the tests are going to look like. Okay, so the exercise was the following. The increasing pressure put upon your mining company by the Environmental Authority regarding the use of fresh water from nearby underground aquifers indicates that sooner or later you will lose the right to continue pumping water from this source. Even though a desalination project is in development, water makeup must be reduced as soon as possible, so you must analyze possible savings in your mineral process. The company you work at is a concentrator plant. One alternative is to increase the percentage of solids of the tailings thickener. One way to do this is to switch to a better flocculant. However, you are aware that this may have consequences downstream at the tailings dam facility in terms of geotechnical stability. So, after finding an optimal flocculant dosage in the laboratory, you decide to analyze the ternary diagram and compare the old flocculant tailings to the new flocculant tailings. So the question is the new flocculant and its dosage adequate for use? Base your answers on both the ternary diagram based on sand composition and the ternary diagram based on FOFW content. Okay, in regards of time, we are only going to use this one, okay? We're just going to work on this one, yeah, because of the time that we have. And this other part, I'm going to leave for you to develop as an exercise. Okay. So let's start off with this problem over here. Okay. So this is a ternary diagram. Okay, so remember that we have different zones here. Okay, this is a fresh ternary diagram. Remember that the red zone, which was located in the in the right side of the chart, where we have a tendency towards fines, was our red zone, or our zone that is restricted. Then we have the blue zone over here. Then we have a transition zone, which is the one that I'm sort of trying to cover here. And then we have the green zone, okay? But besides that, the SFR parameter also helps us determine in which condition we are located in. So what we have to do is basically locate a point locate the old flocculant in this graph, in this ternary diagram, sorry, and then locate the new flocculant in the same ternary diagram and compare them in terms of stability. Okay? So what we have to calculate is the percentage of solids, the FOFW, and the percentage of fines in this system. Okay. So firstly, we already have the overall solids content. I'm looking for something to draw. Okay, let's do it a little bit thicker now. Let's see. Oh, that's nice. Okay. So we're going to do a little table here. Okay, so here we're going to locate the axis value. And in terms of axis value, what we have to locate is the percentage of solids, the percentage of fine over fine plus water, and finally, the percentage of fines. Okay. So in terms of solids, this is going, here we're going to talk about the old flocculant. And here we're going to write about the new flocculant. It's a double C. Okay. Okay, so in terms of percentage of solids, this one is 55% and this one is 60%. Okay. Remember that the fine over fines and water is calculated as, well, first of all, we have to calculate the SFR, which is calculated as 1 times the, I don't know how to do this letter, this strange Greek letter over here, I can't remember what it's called, F, okay, but this is basically the fraction of fines in the system, okay, and by fine, I mean the particle that is determined, the fraction that is determined using this standardized mesh over the percentage of fines. And then the FOFW is calculated as the percentage of solids times the fines fraction. So I'm going to erase this a little bit so we can keep calculating here. We can write it later. Where are we? Okay, this and this is calculated but times the fraction of water, which would be 1 times the percentage of solids plus the percentage of solids times the fines fraction. Well, I'm drawing that letter worse each time I write it. Whatever, okay. Okay, so let's start with the SFR. We're not using the SFR here, but it does help us draw some conclusions, okay? So first of all, let's calculate the SFR, and this would be 1 times 18% over 18. And this is equal to 4.56. Okay. And then now we're going to calculate the FOFW, and this is 0.55 times 0.18 divided by 0.45, which is 1 minus 0.55 plus 0.18 times 0.55, and that equals 18%. That's just a coincidence, okay? It doesn't have to come out like that. And finally, we're going to calculate the percentage of fines, and that value we already know is 18%. Okay, that was from the data. This one's directly from the data, and this one is also directly from the data. Okay, so these are the conditions of the old flocculant. So now we're going to determine the conditions of the new flocculant. Okay, I'm not going to repeat the formulas. I'm just going to give you the final values. Okay, so this is a percentage of solid that comes from the data. The FOFW in this case is 23%, and the percentage of fines is 20%. So now we have these sets of data. Oh, and the SFR finally is 4. Okay. So now what we're going to do is we're going to locate our data in our ternary diagram, and we're going to start off with the old flocculant. So the old flocculant numbers are percentage of solids, 55, FOFW, 18, and the percentage of fines, 18%. Okay, and as for the new flocculant, percentage of solids is 60, the FOFW is 23, and the percentage of fines is 18%. Okay. So now we're going to locate this data over here. Let's start with the old flocculant, okay? Okay, so there are several ways of doing this, but the easiest way is to basically form a triangle and then draw bisecting lines towards the opposite face of the vertex, okay? So let's start, insertar. Going to use a little star here to locate these points. Okay, so our first point is 55% solids, which would be over here. Then the fine over fine plus water fraction was 18%. So that would be, oh wait, where is it? So that would be somewhere, I don't know, over here, I guess. Okay. More or menos. And the percentage of fines was also 18%. Remember, that was a coincidence. It doesn't have to necessarily turn out that way. Okay, so with this, I'm going to draw the triangle. Okay, let's draw the triangle here. Then here. And finally, here. Okay. And now I'm going to draw the bisecting lines in order to locate our point. Okay. So I don't know. So this is better if you do this with a ruler, it's much easier. So remember to bring, would you say that's half? Yeah, okay. Let's say it is. Then over here, okay. Oh, okay. Let's trust our magical interpolation powers. And then over here. So our first point is located here. So this is the blue star. Okay, the blue star represents the old flocculant. I don't know if it's with an E or with an A, but it doesn't matter. Okay, so now for the other one, we're going to use a red star. And yeah, okay, let's choose a red star. Let's change the color. Let's say, or maybe a black star. Okay. So the black would represent the the new flocculant. Okay. So this case, we are located here at 60%. Then it was 23% of the new flocculant, which would be, I don't know, somewhere around there. And the percentage of fines was 20%. Why? I didn't want that. It came out blue. I wanted it black. Okay. Eat the moment. Okay. So now I'm going to draw the lines. And this is supposed to be a black line. I'm going to make it a little bit wider. But I can't tell the difference there. Okay. So blah, blah. Then the next line is here. We're drawing these over here. And for our final trick, I'm going to do this. Okay, with the line a little bit thicker. And now we're going to use our magical interpolation capacity to draw straight lines. Okay, so that would be here, black line, and then another line over, yeah, let's say that's half. Oh my goodness, would you say that's half? As I said, this is, you know, if you do this with a ruler, this is going to come out a lot better than what I'm doing. Come on, man. And our final line is going to be over here. Okay. So our little black star. Oh, the black star. Okay. And so we're going to be located somewhere over here. Okay. Okay, so first of all, our point definitely moved, but it moved very little. Okay. Our SFR is actually bigger in for the old flocculant than from the new flocculant. And on the other hand, both apparently are located in the stable zone. So let's look at I'm going to compare this. Wait, I'm going to copy this. Give me a second. We're going to copy this and we're going to compare it to the material that we saw last week. And so I'm going to stop sharing now while I look for last classes. This was topic 4. Wait, give me a second. We're almost done, okay? We can start our weekend. Do you guys have any classes next week? Do you have any activities or stuff to do? Fiestas Patrias, you...
No
We don't have
classes.
No, you're not doing anything? Why?
Yeah, we have to. It's like we have a lot of traveling to do.
Oh, you have some... Okay, okay. Wait, I forgot. But you know, you still try to enjoy yourselves next week. You're young. You have to take advantage of that. Okay. So let me share this and we'll be done in a minute, okay? Okay, so now we are looking at so we're looking at both ternary diagrams. And first of all, as you can see, both apparently are located within the green zone. What would you say? They're located in the green zone. Or in worst case scenario, I guess they could be very close to the transition zone, but still they're both located in a stable, more stable area. Okay, so the different conclusions that you could draw from this exercise is that both would produce stable tailings once deposited. That would be one thing. And from the point of view of the SFR, remember that we have the SFR parameter, where they're both located in this zone where the SFR is over 3. Okay, so in that case, both of these tailings would be relatively good. So maybe in terms of improving settling conditions or stability, they're both very much equivalent, but the second choice, the use of new coagulants, since we're talking about a higher percentage of solids, might be a good choice, okay, because it does allow the recovery of an additional amount of water. Okay, remember, the more the solids that you have, the more water that you will be able to recover, okay? Yes, that's right. Okay. I'm just going to save this. Stop sharing. And that would be all for today. We have finished at 11:28. 2 minutes before I said so. Okay. So before we go, do you have any questions? I am going to upload this video because this is supposed to be taping, I think. I hope it did. I can't. Oh, yes, it's taping. So I am going to upload the video or share the video so you can have this material to continue studying. And I'm also going to upload the spreadsheet and the document with the developed exercise. Okay, I might not upload everything today because I have something after this, but you will have the material probably during next week. Okay, so do you guys have any questions?
Hello, Paula.
Yes.
Yeah, sorry. Concerning the first assignment, I don't know, but unfortunately, I didn't see any place to upload it on Aula. So I sent it.
Can you please upload it to Aula? I know you sent it to me, but can you please upload it as well?
Sorry, where exactly on I was supposed to upload it? Because there wasn't any.
I thought the teaching assistants had done something. Wait a minute. Let's look for it.
Okay.
Because maybe it's not visible. Let me see. Just give me a moment. You guys are 201. Okay, so I'm looking for it. Here it is. Okay, I'll show you. Just wait a second. Okay, so this is your Aula 201, parallel 201. So under Unit 1, if you go to the bottom, you'll find this.
Okay.
And it's visible and everything. Let me see if everything's okay. Yep, no, everything's good. Okay, so you should be able to, let me see here. Yep, that's where you upload it, okay?
Okay, thank you.
Okay, no, you're welcome. Okay, do you guys have any more questions before we go?
Regarding the submission, do we submit the whole video or can we just submit a link to the video?
Oh, should probably upload the video, but if it's too heavy, just upload the link. But please make sure that it's open to, I mean, it's accessible. Try to upload the video, but if it's too heavy, just upload the link. It's okay.
Okay, maybe in OneDrive. Okay, thank you.
Okay. Make sure it's available to be able to be seen by us. By
Okay,
us, I mean the teaching assistants and myself.
okay.
Okay.
Thank you.
Okay. Yes. That.
Hello.
Yeah.
Oh,
The instruction says that only one person will upload per group.
Yes.
So what
Yes.
will the other people submit? Like just leave it.
No,
the
nothing,
assignment.
nothing. I mean, in the video, it has to be clear which are the members of the group.
Okay, so we'll just leave the assignment blank for the other members.
Yes, so just upload
Okay.
one. Just select one of the 2 or 3 of you to upload the video, but make sure that the video it's clear who worked on that. Who the members of the group are.
Okay.
Okay.
Professor, I want to ask something.
Yes.
Yeah, I'm actually our video is little bit more than 3 minutes. Is it okay? Like around 3:40? 3 minutes 40 seconds.
Sorry, 3 minutes. It's supposed to be 3 minutes.
Seconds.
No, it's
Yeah,
too
but
much.
yeah.
But if it's what came
Okay.
out, okay, we'll see what we'll talk to the assistants and see what can be done. Okay, but the idea was to be within the 3 minutes. Okay.
Okay.
I mean, you're not going to get a 0, okay? It's okay. You might get a small reduction in the final points in the final grade, but you're not going to get a 0. I mean, you're delivering. You did the job. You might get a small deduction in the final grade for that.
No. Okay. Thank you. I will edit it.
Yeah, but you're not going to get a 0. Okay, don't worry about that. Any other questions? Okay then, so that's it for today. And have a nice week. Have a nice time. Try to get to know our Chilean culture and enjoy and stay safe and study if you have to, of course. Okay. Okay,
Thank
bye
you.
everyone. Take care.
Bye.
Bye-bye. Bye.
Bye bye.
Bye-bye.